So today we're looking at hypergeometric distribution, and don't let the name scare you. It's pretty straightforward. So best way to explain this is by starting with an example. So let's say we have 4 red marbles and 3 blue marbles. And if you randomly select one marble and repeat 4 times, so if we pick 4 marbles, but assume no replacement, what does that mean? They're no longer independent. So right there, if you remember binomial distribution was a repeated task, but with independent trials. In this case, they are dependent trials. There's no replacement. So what is the probability that you select a red marble twice? So we have x equals 2. So calculate the probability. So we're going to explore this problem by calculating the probability tree, just like we did with binomial distribution. Okay? So we can calculate the probability, which is NA over NS, which is the number of ways to select 2 red marbles multiplied by the number of ways to select 2 blue marbles divided by the total number of ways to select 4 out of 7. And if you look carefully, we see that this number of ways to select 2 red marbles out of 4 is 4 choose 2. And then the number of ways to select 2 blue marbles out of 2 blue marbles out of 3 is 3 choose 2. And then finally, the number of ways to select 4 out of 7 is 7 choose 4. And that's how we calculate the probability. So we said that, we calculate the probability, then we draw a probability tree. So we calculated the probability, which is 4 choose 2 is 6, 3 choose 2 is 3, and 7 choose 4 is 35, which is 18 out of 35, which is, 51% probability that we will select 2 red marbles out of the 4 marbles, out of the 7 total marbles, but out of the 4 red marbles. And here we have our probability tree. So we could either select red or we could select blue on each case. Of course, the probabilities are different. It's 4 out of 7 on the first try and 3 over 7 on the next. Now, the next try we have 6 marbles, but only 3 reds, because we picked one up here. And we still have the 3 blue in this case because we didn't select a blue marble. At the bottom, we see we still have 6, but we picked a blue, so we have all our reds, and we have 1 blue missing. And we continue on to see our probability tree right there. Okay. And essentially, how many paths represent 2 marbles? Well, here are our paths. So these represent 4 red marbles, 3 red marbles, 3 red marbles. So we've been through this before. We just count the number of paths. Okay, so how many paths have 2 red marbles? Well, there's 6 ways. There's 6 paths. But are the probabilities the same for each? No, take a look at that. It's 4 over 7, 3 over 6, 3 over 5, and 2 over 4 and 1. And here we have 4 over 7, 3 over 6, 3 over 5, and 2 over 4. So they appear to be the same. Here we have 4 over 7, 3 over 6. But here we have 2 over 5 and 3 over 4. Okay, so it's not the same. So it's a little bit more challenging to convince ourselves that to do the same thing. Like we can't use trials and successes in that fashion. But if we calculated the probability, okay, so if we calculated the probability of each scenario, we have 0 reds, 1 red, 2 red, 3 red, and 4 red. It's a lot easier. So how many ways can we choose 0 reds? Well, 0. How many ways can we choose 1 red? Well, it's the number of ways of picking red times the number of ways of picking 3 blues, which is we can choose 4 different red marbles, or we only have one choice. We can only pick 3 choose 3 over 7 choose 4. We calculate this probability. It's 11%. We can do 4 choose 2 when we have the probability of selecting 2 reds multiplied by 3 choose 2 all divided by 7 choose 4. When we do that math, 4 choose 2 is 6, 3 choose 2 is 3, 7 choose 4 is 35. We get 18 over 35, which is equal to 51%. Here we have the probability. Number of ways we can choose 3 reds. Well, for every, we have 4 reds, we choose 3. Then we have 3 blues. We only need to choose 1. How many ways can we do that? And once again, the denominator stays the same. 4 times 3 over 35 is 34.3%. Let's clear our pen markings for now. And how many ways can we select 4 reds? Well, 4 choose red multiplied by, I'm not choosing any blue, so there's only one way to choose no blues. And that's, the denominator stays the same. That's the number of ways to pick. 4 out of 7 marbles. And that's 1 over 35. Now, if you add these up, you'll get 100% because it's our full distribution. And if we were to calculate these, we just set it for 0 is an option. 1, 2, 3, and 4, right? But there's a 0% probability here. About 11% right there, just over 0.1. For selecting 2, it's 0.5. And for selecting 3, that's basically 34%. And finally, selecting 4, what's the probability that you select all 4 reds? Well, that's a very low probability. It's about 3%. Okay. So just in general, here's the formula. A probability of X successful outcomes in R dependent trials is P of X is number of available successes. A is a number of successful outcomes available. So available successes, right? So in the red marble example, we had 4 red marbles, right? This was always 4. What's n minus a? Well, that's the remainder. That's the number of non-successes, right? Total minus number of available successes is the total number of available failures, so non-reds, right? And then this is r minus x. It's basically the total number that you're going to select, the number of trials. R, do I specify? R is number of dependent trials, right? Subtracted by the number of solutions. So it's basically the remainder. And then this is total ways to do it. So it's just what we learned previously. It's just taking the number of trials and choosing the number of available successes. I think this is better explained with an example. So in this case, if we said, what's the probability? If we had, let's give an example. Let's say we had 7 red marbles and 6 non-red marbles. If we selected marbles 4 times, what is the probability of red being selected 3 times? Well, in this case, let's look over the formula. P of X is 3. In this case, what's A? Available successes. So how many available reds do we have? 7. What's X? Well, we already defined X. What about N? Well, that's the total number of marbles we have. So 6 plus 7, we have 6 and 7 non-red marbles. So that is 13. What's A? What's N minus A? Well, that's just 13 minus 7. R. What is R? That's the number of trials we have. R equals 4. So now we have all of these defined, right? So if we put in our formula, if we want to use our formula, But we can look at it like this. What's the probability of getting 3? Well, we want to choose 7. 7 available successes. We're going to choose 3 out of them. And then how many ways are there to choose the remaining 6? Well, there's 6 remaining. That's n minus r. N minus a is 6. 6 choose. And how many do we want to choose? Well, we're going to choose one of them, right? So r minus x. Let's look at r minus x is 4 minus 3, right? The remaining ones that we didn't choose as successes. That's what r minus x is. And that's divided by, where are we? 13. Choose 4. Right? Total number of ways I can select 4 marbles. And we solve for that, and that's basically how we use this formula. Finally, we have expectation for a hypergeometric distribution. And if you want to think about it, I like to think about it like this. We have available successes, right? So in the previous example that I just did, 7 and 6, right? 7 red, 6 non-red, right? How many do we expect out of 4 trials? If I take 4 trials, how many reds do I expect? Well, in this case, expected value is how many we expect, right? And that's equal to, what's r equal to? Well, that's equal to the trials, 4. What's n equal to? The total marbles, 6 plus 7. What's 6 plus 7? 13. What's a? Available successes. So there's 7 available successes. So essentially what you want to do is you take your trials, multiply it by available, 7 over 13. And essentially, it's 28 over 13, which is 2 and 2 over 13, right? That's how many reds I expect to get out of 4 trials. So a bit more than half. And that's it. That's hypergeometric distribution. Now, this has already been assigned. But, some of the best ways, because the best ways to do this is by example. We're going to do this we're going to do some of these examples, or the homework questions. So let's go ahead and do question 1. So a bag contains 5 red. We have 5 red and 6 blue blocks. What is the probability of getting 3 red? Probability of 3 if 4 blocks are randomly chosen. So that's my successes. So x equals 3, trials equals 4, right? What's n equal to? And let's assume that they're not replaced. So that, because this has to do with hypergeometric. So n is, 5 plus 6 is 11. And how many available successes are there? Well, if we're talking about if success is getting red, so there's 5 available successes. So how do we do this? Well, we could do the formula, but I like to think about it in the probability of getting 3 reds. Okay, well, how many ways can I get? That's NA over NS. Well, NS is easy, right? We're going to choose, there's 11, and we're going to choose 4, right? So that's easy. NA is basically how many ways can I get 3 red blocks? Well, how many blocks do I have? I have 5 red blocks. I'm going to choose, I want 3 of them to be red. And then I'm going to choose 2 more, right? I'm going to choose 2 more from the remaining 6 blue blocks, right? So for every way I can choose 3 red blocks. And essentially, let's rewrite it so that we can, the probability of A equals NA over NS, which is, we're going to write it in this fashion. 5 choose 3 multiplied by 6 choose 2 all over 11 choose 4. And that's basically Oh, we select 2. Sorry, we select 4. My mistake. We only select 1 over there. Sorry, we don't select 5. My mistake. I was wondering why I didn't find my answer. We only select 1 in this case. So it's 5 choose 3. So the answer in this case is B. Because B is found right there. Right there. Oops, not B. Why am I saying B? I meant D. D. Because I have 5 choose 3, 6 choose 1, 11 choose 4. Okay, what is an example of a hypergeometric distribution? That's question 2. So the probability of a number of aces in a 7-card hand. So the probability, how many ways can I get an ace? It seems like A is correct, because when I remove a hand, when I remove a card, the probability changes. The probability of each sum when 2 dice are rolled. Now, each dice is independent in this case, so I didn't call that hypergeometric. Probability of a number being randomly chosen from 1 to 10. Well, that is not hypergeometric, right? Because I could select that same number multiple times. And the probability of the number of times a 3 occurs when rolling a die 6 times. That again would be a binomial distribution because they're independent trials. So the answer is A, just the first one. Okay, let's look at the next thing. Question 3. Each expression represents a probability of a hypergeometric probability. State the values of the unknowns. Oh, okay. So let's look at A. So 3A. So we have right here 6 choose 3 times 9 choose 2 over N choose R. So how many things are we choosing? So if you think about it, we have 6 possible successes. And 9 possible non-successes. So we're calculating the probability that we select 3 successes out of the 6. So x equals 3, right? And 2 non-successes. Assuming we're doing success first and non-successes second, right? So non-successes. Selected. So we're choosing 3 and 2. So obviously the number of trials, R is going to be equal to 5. Because we're choosing 3 and then we're choosing 2. And the total possible is the number of successes and non-successes, which is 9 plus 6. 9 plus 6 over there, which is equal to 15. So in this case, N equals 15 and R equals 5. Now let's take a look at how I did that again, right? So when we calculated this, right, this is the number of successes. And we're choosing 3 successes, right? So obviously we're choosing 3. This is the number of non-successes we're choosing. Oops. That we selected. So we're choosing another 2 out of 9. 9 successes, 9 non-successes, and 6 successes available. So that's the total number of options available. So that's what N is. Okay, so essentially the sum of that equals n, and the sum of that equals n. If we look at the formula, if we look at this formula, let's take a look at the formula from what we said. Okay, let's look at this formula. Not now. I'm busy. Let's look at this formula for a second. I'm going to clear. I said this and this, if we add them, a plus n minus a is equal to n. And I was right. And if I add these, x plus r minus x is equal to r. So if we add these, it's equal to r. And if we add these, it's equal to n. So that's a little bit of discard. That's a little bit that we can see there. Okay, so let's take a look at this B section. We have number of successes that we have, and we have the number of failures. So I'm trying to find this number of failures over 10 choose 6. So how many failures do we have? We have 7 potential failures. And how many available successes? If we have 10 total, then A must equal to 3, or 10 minus 7. And here we have total selections. So that's total selections. 5, this is a number of trials. So 5 are successes, which means B equals 1 to make up that 6. Let's look at C. We have 6, choose 3, times some value, choose 2. And we have 25, choose D. Once again, these two should equal to n, right? So then obviously this has to be, C has to be 19, because 19 plus 6 is 25. All right, and then these two chosen values, that's what we choose, the number of successes and the number of non-successes that are chosen. So D, this D is equal to the sum of that. So D equals 5. So that's how C is done. Let's see, what else is there? Question 4. Question 4 is assigned. Show the hypergeometric probability distribution for experiment with. Okay, so that's pretty easy. A, we just apply the formula. N equals 15, trials equals 4, and available successes equals 7. Right, so how do we do this? P of, well, what's X? Oh, I have to do the full distribution. This requires a lot of work. So I'll do a few, and then hopefully you'll know how to do it. So we have to do 4 trials. So X equals 0, probability of X equals 1, probability of X equals 2, probability of X equals 3, and probability of X equals 4. Right, so we have 4 trials, 7 available successes. So what's the probability of 0 successes if I have 15? So that's basically 15 choose. We're doing 4 trials. That's a total possible outcomes. That's NS for all of them. In fact, that's going to be NS for every single one of these. 15, choose 4, because we have 4 trials out of 15 possible results. And what's next? Well, we have to calculate the numerator for all of them. So essentially the numerator for all of them is going to be something like, total ways to choose successes multiplied by number of ways to choose failure. Let's separate these by a line. Okay, so available successes, 7, choose 0, and then we have to choose out of the remainder I'm just going to put failures here so that I know. Failures. You have 8, right? 15 minus 7. So here we have 8. In fact, all of these will be 7, 7, 7, 7, and we'll have 8 failures to choose from for all of them. In this case, I'm choosing 1. Have the 1 success. In this, and then I'll have how many failures? Well, let's do the 0 first. I'll have 0 successes, and how many failures? All of them, rest will be failures, so 4. Here I'll have 1 and 3. They have to share the number of trials. Here we'll have 2, right? X is 2 successes and 2 failures. 3 and 1. And finally, we'll have 4 successes and 0 failures. Now, essentially, you'd calculate these probabilities, whatever they worked out to, and then you'd graph the distribution. So you'd have, you'd get an amount for 0, you'd get an amount for 1. Let's see, you get an amount for 2, I'm assuming it's the highest, and then 3 and 4. That's probably how the probability would look like. Sorry, 2, 3, and 4. X, I, and this would be P of probability of Xi, and then you graph the probability on this side. Okay, you guys should do the rest of that, and also do B on your own. Next question. We had 6, 7, let's write it here, 6, 7, 9, and 11, so I don't have to go back all the way all the time. So I have in a box of 20 light bulbs, 5 are defective. 5 defective light bulbs. 3 light bulbs are selected at random. No. Three are selected at random. What is the probability that at least 1 is defective? So at least 1 is defective. So N is 20. A being defective is 5 available defects. So how many successes are there? What did we define successes? No, that's right. How many possible successes are there? Well, we have, let's see. How many defects are there? 5 defects. Oh, and then how many trials? That's right. R is the number of trials. So what is the probability that at least 1 is defective? So to do at least 1 is defective, it's 100% minus 0, right? What's the probability that nothing is defective? That's the way we'd solve it. And the way you do that is, well, the probability of 0 being defective is, well, what's NS? Well, we're going to choose 20. We're going to choose 3. So 20, choose 3. And then how many ways can I select 0? 3, choose 0, multiplied by 17, choose 3. Is that it? No, it's not 17, choose 3. Let's do this again. I do 5, choose 0, right? Total of successes available, and I'm choosing none of them, multiplied by the number of failures, 15, and I'm choosing all 3. Right? And whatever that works out to be, I'll do the math right now. P of 0 is equal to 5 choose 0 is just 1. 15 choose 3 is 15 times 14 times 13 times 12 factorial over. And then we'd have 15 minus 3 is 12 factorial times 3 factorial. And we cross that out. And that's equals to 6, which is, I'll just say 3 times 2, right? And we take out the 3 and we make it a 5. We take out the 2 and turn it into a 7. So 5 times 7 over 20 factorial over 17 factorial, 3 factorial. So that's 20 times 19 times 18 times 17 factorial and divided by 6, which is, that's a 3. So let's do it over here. I should just get a calculator, to be honest. 5 times 7 over 20 times 19 times 18. And it's equal to times 13, of course. And of course, these are prime numbers. So I have a 4 there. Boom. 7 times 13, 91. And I believe 91 is prime over whatever that turns out to be, 19 times 18. And then you do one takeaway there to get the probability of at least one being defective. Okay? So I'm not going to do all the work for you just because I can't show a calculator being handy. I have to go through too many tabs. What is the expected number of defective bulbs? Okay, so I was waiting for an expectation question. So we have E of X equals available successes over total, right? Multiplied by the number of trials. So how many trials did I do? I did 3 trials times available defective bulbs multiplied by total, divided by total bulbs. So this is the proportion of available successes to total possibilities, 20. Multiplied by 3 trials is equal to 15 over 20, which is equal to 0.75. So if I pick 3 bulbs, I don't even have to expect 1. I can expect less than 1. Right? If I picked 5 bulbs, I could probably expect, 4 bulbs, I could pretty much expect 1 to be in there, right? Because a quarter of them, look, 5 over 20, right? 1 over 4 of them are defective. So if I pick 4, I can expect 1. Okay, so what is the probability? What is the meaning of P3 in this context? So I'm going to write this out. So it's the probability, let's write it down properly, probability of selecting 3 out of 5 defective bulbs. Oh, no. My God. Let's rewrite this. Sorry, we're going to be careful with our wording because I'm teaching you. So, the probability that all selected, right? So we're selecting bulbs will be defective. So it's like I'm going to choose all 3 are going to be defective. So the first time I select, I'm going to have, right? So think about it like this. Hopefully this makes sense when I explain it. And I'll take my time describing it. So I'm just going to duplicate this a few times. 1, 2. Right? Duplicate. And duplicate. So I'm going to have a bunch of defective bulbs. So that's D, D, and D. And essentially what this says is, what's the probability that I select one bulb and it's defective, right? Followed by the probability. So after that, I'm going to have to select, oh, how many defective bulbs are there? There was actually 5 defective bulbs. And then I select defective. And then I select, what's the probability, again, that I select another one? Now the probability keeps getting smaller each time. And what's the probability that I select a third one? So 3 out of 3 will be defective if I randomly choose. So what's the probability of me doing that 3 times in a row? Okay, and how many ways I can do it multiplied by the ways that I can select the defective ones. Okay, hopefully that makes a lot of sense. Let's do question 7. And then the rest I'll leave to yourselves. 7. In a card game of bridge, 13 cards are dealt to each player. 13 to each player. Find the probability of each of the following hands. So 4 aces. Okay, so how many aces are available? So we say a success is an ace. So we're going to say 4 aces. Available aces, available success is 4. So essentially, what's n of s? Well, it's essentially 52, choose 13. There's a number of ways I can get a hand. So the probability of 4 aces is, how many ways can I choose 4 aces? Well, I can choose, well, there's 4, choose 4 aces, right? And then I have, how many remaining cards do I have left? Well, I have 48 cards left, and I have to choose the remainder, 9. So the probability of 4 aces is equal to 4 choose 4. Oops, let's write it properly. 4 choose 4 multiplied by 48 choose 9 all over 52 choose 13. At least one king. So we'll do B. At least one king. So let's say probability of at least one king. Well, there's 2 ways you can do it. You could do probability of 1 king plus probability of 2 plus probability of 3 plus probability of 4. Or you could do 1, take away probability of 0 kings. So let's do that. Is equal to 1, take away, what's the probability of 0 kings? Well, we could do, how many kings are there? You know, we're going to define success as a king. 4, choose 0 kings, and then there's 48 left, and we're going to choose all 13 from there. All divided by 52, choose 13. And that's your answer. Once you do this calculation, you do 1 minus whatever probability that turns out to be, and you're good to go. Okay, so probability of 5 clubs and 8 diamonds. Okay, so let's do that. So the probability of 5 clubs, 8 diamonds equals, well, the bottom stays the same, 52 choose 13. That's a total number of ways to do it. Now, how many ways are there to select 5 clubs? Well, it's let's see, 5 clubs would be, there's 13 clubs. We're going to choose 5 multiplied by how many diamonds are there? Well, there are 8 diamonds. So anyway, we're going to choose 8 of them. And there's 13 of those, right? And then I think we covered all successes, actually. We covered 13. But just to be thorough, how many are left? 26. And we're going to choose none of them. And there's one way to do that. But just, we didn't even have to include that. But just to show that the formula still counts, right? This is the number of successes. We're still counting successes. But it's 13, choose 5, and 13, choose 8. And there's 26 left to choose from. And we're going to choose none of them because there's only 13 to choose. And that's how question 7 is done. All right, so number 9 is actually quite important, so we'll do that too. I was planning on stopping, but we'll just do this because this is a good example that I might ask also to test. So 200 tags, 200 foxes tagged. In 100 sightings, and you can think of that as a trial. 14 were tagged. 14 tagged out of 100. Estimate the size of the population. So let's see. We can use expected. EX equals, we have available successes over population multiplied by trials, X. So let's take a look at that. So the question is, if we had the whole population and we took a certain amount of trials and we multiplied it, and we should have an expectation. In this case, we got E of X, we got 14, right? Now, it's not perfect, but we just assume that 14 is we got what we expected. Now, we have to assume we got what we expected. Now, sightings is trials, right? So X is 100, right? And finally, available successes is 200. So essentially, we should say 14 equals X is 100 times A, which is 200, over N, right? So we could say 14N equals, well, let's just write it out like this. 100 times 200, divide by 7. We can divide that by there. So we have N equals 10,000 over 7. Well, 10,000 over 7. Let's get out a calculator so that we can have 10,000 divided by 7 is actually equal to about 1,428. Let's just round it to or 29 actually, because it actually rounds out to a bit higher. So think about that, right? If we had 200 available tagged foxes and we trialed, we tried for 100. We tried to see 100 and we only got 14. That means, if there were 1,000, we would have got 140, right? So there's a proportion of what you could expect based on the trials you take. Anyway, that's it. So you do one more by yourself. I think it's question 11, but that's it for this video.